this afternoon's seminar that will be presented by Professor Stefan Seelecke from the Intelligent Materials Systems Lab and from Saarland University. I had the pleasure of visiting his lab, I think about 5 years ago, and beautiful place, and right on the western side of Germany, and with wonderful equipment and set up and doing some really good precision work in the area that we are very, very dedicated to here, and that is artificial muscles and smart materials and other materials that change shape and with heat and electricity. So Stefan's going to talk about this. I'd like to say that in history, he did some time at MIT, postdoctoral work there, is that right? But you're from TU University, Berlin, I believe, Technical University Berlin, and then it was off to North Carolina State University. And that's when I first met up with Stefan, when he was with that university, and that was at ASME meetings in the United States. And he managed to get me to take his place on the SMASIS committee, didn't you? It was a very clever move, because then I had 3 or 4 years of work to help to arrange the conference and got out of it. So now I'm going to get even with him and get him to talk now. Anyway, but so he then went over back to Germany, to Saarland, and then set up this place, the Intelligent Materials Systems Lab, where he's running it. He's here with Bettina, his wife, Bettina Fassol, his wife, and Marlene, daughter. They're staying in, located, domiciled in the 5th floor lab, and doing really neat research project with us right now. I don't know if you're going to talk about that, but maybe you could perhaps mention it. And so I'll hand it over to Stefan now, and I'm sure you'll be entertained by what he's going to tell you in the world of smart materials. And not stupid materials, smart materials.
Thank you very much for the kind introduction, Ian. Yeah, it's a great pleasure for me to be here, and actually I'd like to thank for the possibility of not only giving the talk, but also to spend time with one of the leading labs in dielectric elastomer research, and also get time to explore this great country. And Ian already gave half of my talk introducing myself, so I just briefly skip over a lot of this here. So we're affiliated with the Department of Systems Engineering and also Material Science and Engineering, and the work that we do is right on the border between these two. We also are part of the Center for Mechatronics and Automation Technologies in Saarbrücken, Germany, which is run by the university. That is more like an applied research center, while the basic research that we do, we typically do this through the university. To give you a better idea of where this is, so Saarland is one of the 16 states of Germany, and it's right on the border to France. So right here is where we are, and you see we're not really in the center of Germany, but we like to say we're in the center of Europe. As a matter of fact, if you want to go to Paris, it's less than 2 hours with a high-speed train. If you want to go to Berlin, the city, the capital of Germany, it takes you about 6.5 hours with a high-speed train, just to get you an idea between Germany and Europe. So our lab actually is located in like old ABB premises. So that used to be a plant for production of electromotors. And when I looked out of the window, I already saw one of the ABB signs around here too. So that's a pretty ubiquitous company here. And so it's been, once they left the place, Saarland took over, and it has been home to some startup companies and now to the Center for Mechatronics. So we're basically in this huge research park here. You kind of see a little bit the old industrial atmosphere still gleaming through, and these are part of the labs and the offices that we're using. So also I can stay very short. Ian was already so nice to give an introduction of what we did here. So Berlin, USA, all of this through. So maybe this was the opportunity to meet up with Ian when I chaired the ASME conference on smart materials, and basically just cost me a few drinks and cost him 4 years of his life, just like he said, right? So we also, in Germany, we have similar structures. We also have like technical committees within the German Engineers Association on smart materials, and that's basically one of our work. I'm chairing the one on smart materials and systems here, is to further the widespread use of smart materials. And what this really is, it's basically, I'm trying to give you a little overview here today with a talk. Before I do that, I'd like to introduce my team. So we're currently about 3 postdocs, about 13 PhD students, and most of them are in the picture. A lot of master and bachelor students, research associates, lab engineers, and 1 administrative assistant, which basically do all the work that I have the opportunity to present to you. So what is it that we do? So we already talked about smart materials. Our aim, our goal is the development of mechatronic actuator and sensor systems, which are using smart materials. Amongst those are shape memory alloys, dielectric elastomers. Most of you will be familiar with piezo materials. Shape memory alloys can be either thermal or magnetic in nature. MRF stands for magnetoreological fluids. All of these are materials that can change their shape when you apply some external stimuli, and that can be used either for actuation or the other way around. When you change their shape with some mechanical forces, you generally produce electrical signals that you can use for sensing. So for us, our aim is, as I mentioned before, is try to introduce how to develop new novel systems with these materials that do actuation and sensing. And so we do a lot of system application development where we try to help companies and other interested partners in building better systems which could be more energy efficient, lower cost, lower weight than standard actuation devices. If you think about it, everyone's familiar with electrical motors. But if you want to build a linear drive, you take an electrical motor, you add gear systems, push rods, becomes fairly complex, and sometimes it's much easier to use a material that adapts its shape to do something. And I'm going to give a few examples of how we do this in the future. Also, we work a lot, as I mentioned, with industrial companies, and so we tend to use commercially available materials, shape memory alloys. You can buy them from several suppliers worldwide. Dielectric elastomers, just like Ian, we make them ourselves in the lab, but we use maybe thin films that are commercially available from Wacker Chemicals, for instance, or Parker in the US. So that once you do a project with a company, that you can also show them a road to a potential product afterwards. So if you basically just do everything in the lab, you can only do a few meters, and then the company will lose their interest very quickly. So most important, though, however, these materials need to be characterized, so we build our own testing equipment and test rigs. You see an overview here of a few of these things in order to characterize the materials so that we know how to design systems afterwards when you require a certain stroke and a certain force, for instance. So also we do develop mathematical models for system design and also for control applications for these materials. And then last but not least is electronics development, because most of these materials use some non-standard electronics. I mean, if you have a stepper motor, you go to the electronics store and you get a card to drive the motor from your computer. For all these materials, that is not yet available. So a lot of the research work that we also do is dedicated to developing suitable electronics. I'm going to say a few words about that once we come to it. So in terms here, we have a clean room available where we actually produce the dielectric elastomer actuators and sensors. We have a lot of 3D rapid prototyping system, 3D printers. You see some of those here. Then we have all kinds of environmental testing chambers and thermal and optical camera systems to characterize the materials. So let me start with dielectric elastomers. This is also the area that Ian's group is doing research with, so I'm going to keep it a little short, just a brief explanation again. Dielectric elastomer typically looks like a little sandwich. Starts with a dielectric elastomer film, typically on the orders of maybe 20 microns up to 100 or maybe up to 200 microns thickness. And you have electrodes deposited on the top and the bottom. And these electrodes, when you apply an electric voltage, this thing should remind everyone with little electronics background of a capacitor. but it is a capacitor with a variable geometry, because there are also mechanical forces involved. Once we apply an electric voltage, there are going to be attractive forces between the electrode, and with the dielectric being a compliant film, what happens is this. It squeezes the film together, reduces the thickness, and increases the area. And that is a mechanism that the mechatronics person sees directly as a means of actuation. So how do we build actuators with them? One example is here. This is the dielectric elastomer film. We print electrodes onto the film. These electrodes are typically made with a mixture of carbon black and PDMS silicone. The film itself also, I should have mentioned that, is also silicone that we use. So the electrodes bond nicely on the silicone, but they can also deform over a very large stretch range, which is very important, because if you want actuation from it, you have basically the two competing effects of providing good electrical conductivity while also providing a large mechanical deformation, which typically doesn't go very well together. But this mix kind of like guarantees that we can find a good compromise, and so this is why the electrodes are a fairly important contribution to a dielectric elastomer. Then we also put a frame onto the membrane, because otherwise, you know, from your experience in the kitchen, you take your cling wrap and it just tends to do everything you don't want it to do. But so you need frames in order to provide handling, and you also need to have something where you can connect mechanical devices, little push rod cylinders, something, whatever you want to do with it. And that eventually leads to dielectric, what we call a membrane dielectric elastomer actuator. So just a few words, high voltages needed, right? The electrical field that you need here is on the order of maybe 100 volts per micrometer. So if we're talking about 50 micron film thickness, we easily have 1, 2, maybe 3 kilovolts of voltage needed in order to make use of the effect. On the other hand, there's only very low current consumption. There is a little leakage current because none of the dielectrics is perfect, and also then you're just kind of like charge and discharge, basically a capacitor, and this is the only current consumption. So typically you have devices which have high voltage but very low current, still leading to very low power consumption. So oftentimes we're talking about milliwatts when we talk about these devices. And as you kind of like deduct from how I describe it, it's silicone material, it's carbon black, also more PDMS, it's printing, so it's also offers a road to low-cost manufacturing of these materials, and that all starts to make that quite interesting for applications. So here's something we're skipped across. So if I show this again in order to make it work in terms of actuation, we have the sandwich that I mentioned before, and you see that you can also get, like, even though it's a membrane, you get out of plane actuation from it if you place some kind of a bias mechanism underneath. In this case, that's a little spring. And the spring deflects it out from the plane, and then when you apply a voltage, the material gets compressed and the spring can actually push it up a little, and when you remove the voltage, the elastomer compresses the spring back to its original state, and you see you get some kind of pumping motion, valve operation, something like that comes to mind immediately. Nice feature is that it'll do that at very high frequencies, so actually up to the kilohertz range. We have an application of loudspeakers as well, so it really goes into the acoustical range. So other than that, it also provides sensing capabilities. So this is something I'm not going to say too much about because Ian is actually the expert here, so he even founded a company called Stretch Sense, which is located here in Auckland, which commercializes materials through this effect. How it works, you just deform it mechanically and you change the capacitance of this capacitor, and basically you can correlate the change in capacitance to a number of interesting physical quantities like deformation, stretch, pressure, and this is something that can be also made in a very similar way from a silicone membrane and electrodes, and you can add electronics to read out the capacitance change. You can come up with very interesting sensors that have properties that you don't find very quickly with other sensors, because you have very large deformation capabilities and still a very high and accurate readout. Here's an example of a sensor that has a length of 100 millimeters, but it can read down to several micrometers, even though you can deform it up to almost 100%. So how do we make those? Quick overview is here. So I mentioned we had a clean room where we print electrodes, and we use a screen printing method. So you see a properly prepared screen here. This is the printing of electrodes, which is happening. You have to put the electrode material onto the screen. Then you have a squeegee that distributes the electrode material. The screen is lowered onto the silicone film. And then there is a pressure squeegee that presses the material through the holes in the screen and transfers the material onto the silicone membrane underneath. And when the process is done, you basically see the electrodes that I talked about. And the process basically gives you the freedom to have all kinds of geometries that you need. So depending on your application, you basically prepare the screens with a proper geometry, and then you can print whatever is suitable on one side. You put it in the oven, cure it, then flip it around, print it again on the other side, put it in the oven again, cure it, and then you've got like electrodes on a silicone membrane. The process is interesting because it's something that is well established in a number of other industries, electronic circuit boards, t-shirt printing. This is easily scalable for mass production. And the other nice feature is also the frames that I talked about earlier. You can also print them if you find suitable materials that bond nicely with the silicone. Here, that's a special type of epoxy that we identified that also needs to be cured on both sides. But afterwards, you have a complete actuator that I showed you before just come out of a screen printing operation. So very flexible, scalable, low cost. That is what I think is creating a lot of interest in these materials. So here's some application ideas. Here you see one project that we did actually with ABB. So we basically took one of their contactors, the breaker switches that we use for their circuitries, and we set up like a mechanism with these membranes that you saw. And one of the requirements here is mostly it has to be very, very fast. So it's in the order of like several milliseconds. This has to actuate, and we could show that with the silicone and the proper design of the system that is well capable of fulfilling the requirements. You see the voltage input signal, you see a very sharp output signal, which is the exact performance line with typically used solenoids. So this is something that maybe in the future could be one type of application. Another application, very interesting, are valves. So here you see a prototype of a little microfluidics valve that we did together with Burkert, a company that makes valves. So we basically took their original valve, took the solenoid off, characterized force and stroke under relevant mass flow rates and pressure differentials, and then we designed the DEA system accordingly. And when we put it together, afterwards we could show that there is a huge potential for energy conservation. We looked at a process where for a second and a half you open the valve and then you close it again. When you do it with a solenoid, you have to apply constant current. And you easily see here, this is the power that you input, 1.5 watts over a period of 1.5 seconds, gives you an energy consumption of 2.25 joules. When we do the same thing with the electroactive polymer, we see that current is only needed to charge the electrode. So there's a little spike here at the beginning, and when you discharge, you could theoretically even get some energy back, even though this is very small amounts in this order of magnitude here. But when you zoom in these curves and blow up the little spikes, you see here's a little area. When you calculate the energy that you need to do that even without taking into account that we could harvest some back here, is on the order of 5.7 millijoules. So there's a factor of roughly 400 or 500 in terms of energy conservation that would be possible for such an application. Also, we found out that even though the original valve was just designed for on-off operation, we could easily control the valve proportionally by just adjusting the voltage. So we can not only have it being on or off, but we can say 25% off, on, or 75% on by just adjusting the voltage and then controlling the flow through the valve without any further design changes. And we can make use of the sensing properties that I mentioned before. We can basically question the membrane and ask about its capacitance change. It will report it back to us, which we can relate to the amount of opening that we just controlled. So you can build a complete closed-loop feedback control around this device without any additional external sensors. And these are the type of properties that make the technology quite interesting for these type of applications. Here's a larger valve that you see. The one that we saw before was microfluidics. This is one that goes up to a flow rate of 160 standard liters per minute, or up to 6 bars. And you see that's just as possible to just design them. They work exactly like an electromagnetic counterpart would do and have the same performance. Then we were trying to explore the limits. I mean, where they were all like little membranes, thin membranes, and you kind of start to think about, like, you know, how much force can you get from it? And the answer is, from a single little membrane, we're talking about several hundred millinewtons. But if you put them together, you stack them, and you start to look into how to design the bias system that we talked about, you start to look at the mechanical behavior of the material, you find that there are special nonlinear bias mechanisms that you can put together in a nice way. And Stefan, one of our former PhD students, now a postdoc with the lab, was able to put together an actuator that you see here, quite small, has a footprint of 86 by 86 by 16.5 millimeters. And it's able, as you saw, to lift 100 newtons over a range of 3 millimeters, and also work against springs here quite nicely. So you can move the limit. I think he just basically moved the limit of currently known membrane actuators by 2 or 3 orders of magnitude with this, and we published this in Extreme Mechanics Letters, and that is probably right now the world record in like membrane actuators. So lots of other things you can do. One application I mentioned before is acoustics. So here we built a large membrane, and we studied the vibrations of the membrane with a 3D scanning laser vibrometer, looked at all the modes, the mode shapes that we get, and then we start to see something interesting. We just basically applied for a project where we tried to make use of the fact that these modes that you see here, that correspond to certain spikes in the frequency spectrum, they can be maybe compensated for when they provide nonlinearities, or can be enforced by a certain design of the geometry of the electrodes. We're printing the electrodes basically in an arbitrary way by making the screens, and if you want to emphasize a certain mode, you can just print the electrodes in a way that you don't do just one electrode as we did here, but you can segment it, and you can basically have several electrodes. And what we'd like to study is, like, how far can we improve the acoustic properties of these in the future. So here's another example of a loudspeaker. Let's see if I can get this to work here. Yeah, so we have a little movie, and I'm not sure if I can get the sound out of this thing here with the VGA. Yeah, that might work. So that's the work of one of our other PhD students, Daniel Bruch, and he presented this at the Euro EP, one of the largest So he built a loudspeaker from those by using the same type of technology that I showed you before. And so he used these little membranes, and he used not springs but a magnet, a combination of repelling magnets to bias this. And then he puts it together in the following way. This is the magnet that goes onto the frame. Then there's another magnet that goes onto the membrane. And then when you put everything together, that's basically the bias mechanism, and you can design the magnets in a way that you basically get the right mechanical behavior. And then when you look at this, you basically vary the signal by just playing the, let's see, an MP3 file, convert the voltage to high voltage, and feed the membrane with it. And then the deflection is going to simply work and generate an acoustic wave that is transmitted through the air. So you need special electronics for this, so we added like a DSP that does the signal conditioning, and then we fed it into a high voltage generator, and we put all this together. And when you run it through LabVIEW, you can see like how the signals from the MP3 files are converted to current and voltage signals as needed. And here's basically the final prototype that we built, 3D printed casing. So, and it's basically generating music. Here you see the motion of the membrane that we discussed before. And so you basically have a way of maybe building new loudspeakers in the future, which can be adapted to all kinds of geometries by simply printing them in the right way. If you think about this being membranes, you can maybe even stretch them over, let's say, arbitrarily shaped bodies and provide sound systems in the interior of your car or something else. So this is a little overview of dielectric elastomers, and now I'd like to move on and give you an idea on shape memory alloys, and these are the two materials that I'd like to cover. So just for record keeping, you're about halfway through. Let's start with shape memory alloys. How do they work? I'm not sure how many of you are familiar with the shape memory alloys. How many of you have had a shape memory alloy in your hand before? Okay, that's a fair percentage. So here's how it works. You have a material, you saw that was a metal that was actually a single crystal from copper, zinc, aluminum, and you bend it just like steel. And that's not unusual, but the unusual thing is this. I dip it into hot water and it restores its original straight shape. So it looks as if it remembers its former shape, and that's where the name comes from. You can also give it all kinds of shapes. So here's a spring that we made from nickel titanium, and you can stretch that largely, and I dip it in the water and see what happens. It just immediately remembers that it used to be a short and compact spring. So this is something that is very interesting. We're also, the other thing is here, we're pulling on this and we get all kinds of interesting temperature signals. I'll come back to that in a second. So I'm just going to go and skip over this here and tell you how we're going to use this for actuation. Of course, when we want to actuate something like this, we're not going to use hot water or air or torch or something like that. We're going to pass a current through the wires. And just exactly what you do when you switch your toaster on, the joule heating of the current is changing the temperature. And what you see is like temperature goes up and then the material contracts. So when you pay close attention to physics, then you're kind of starting to wonder, how's that? It's a metal and you heat it up and it contracts. Didn't we learn that metals expand when you heat them? And of course they do that too, but there's an additional effect here. So in addition to the thermal expansion of the material, there is a phase transformation going on in the material. And this phase transformation changes the crystal lattice structure from what's called martensite to austenite. You might have heard that in the material science classes. That's very familiar also in steels. And it's that change from austenite, which has a shorter crystal lattice, to martensite, which is longer, and back and forth, which allows you to actuate the wire. And when you contract, it changes into the short austenite at high temperature. And when you switch the current off, it cools off again, and then the weight restores the original shape. So here's a little movie again, showing that behavior. And if you look at this, you'll see that we have 10 kilograms that are easily lifted up by a 500 micron wire. So that's 0.5 millimeter in diameter. And just by heating this wire and contracting the wire like an artificial metal muscle, we're performing a lot of work. As a matter of fact, shape memory alloys have the highest energy density of all known actuation mechanisms. Right? So that means that you can perform the most work from a given volume. Why is this? It's because all the atoms take part and contribute to the motion and the actuation that we see. Right? Typically, you have a motor. If you think about your electric motor, there's only a little bit of the material that's actually generating the force. There's a lot of infrastructure around it that you need. And here, you have each and every atom changing its place. It's a non-diffusive displacement that these crystal lattices undergo. And they're generating a little bit of a displacement at the lattice level, but a very large force, and that is what we saw here. So this is what makes these things interesting. So here you see an example of some measurements with those, and I'm not going to go through all the details of the measurements with you. This is a little setup that we built to measure microscale wires down to about 25 microns is what you get, so 500 microns that you saw in the movie was on the upper end of commercially available actuated wires. 25 microns, it's like a quarter of the diameter of your hair, is on the other end of the spectrum. So what's important, the only thing I really want to show you here is that you do a characterization in order to get an idea of the stress-strain behavior. And that stress-strain behavior depends on the temperature or on the electric power that I apply to the wire. So we run a lot of tensile experiments under fixed powers, and you see that at 0 power it moves up on what we call the martensitic branch over here, and the more power we input, you see the behavior changes so that we have a large hysteresis for medium power levels in between, and when we go to very high power levels we move up on these branches. This is where the material is in the austenite, here's where it is in the martensite, and in between that is the range that we use for actuation. What's also very interesting is if during that very same experiment you also record the electric resistance, and this is shown here. And you see a lot of interesting things from the resistance behavior. If you look at the electrical resistance is what? Resistivity times length divided by cross-sectional area, right? So there are 3 mechanisms in the resistance that basically contribute to change. And you can all see them in this diagram. So when we start here, this is the change in electrical resistance during this experiment at 0 watts. So this is stretching a martensitic wire and unloading it. And what you see is the simple geometric change in the resistance of the wire. So basically it's a strain gauge effect that you have, right? So then I apply 100 milliwatts and I repeat the same experiment. You hardly see a difference here on the mechanical side, but the resistance jumps up by a notch and undergoes almost the same range, and the jump is due to the temperature dependence of the resistance. So I now see the resistance has the 2 mechanisms of deformation dependence, changing L and A, and also the temperature. But even more, when I increase this to the level where it starts to transform into austenite, it also the phase transformation comes into play. And so it's phase transformation because austenite and martensite have different resistivities. So you have phase transformation, you have temperature dependence, and you have deformation dependence. And so the other interesting observation that we make is that also the strongly hysteretic behavior that we see in the mechanical picture completely gone. So when we measure 34 ohms, I can read off and I know the wire underwent 3.6 some % of strain. And if I go here, this is regardless of whether I'm here, 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 or here. So I can use the resistance reading from a simple wire as a position sensor. And I can set up a mechanism, again, where I lift weight and I can control it without external sensors by building like closed loop feedback loops here, and have basically a very compact system that provides a lot of energy and work output and also provides its own sensing mechanism. So here's one example of how you can build systems that might be of interest maybe in the future. So this is a suction cup. So typically if you take sheet metal or glass or wafers in electronics, people use suction cups that generate a vacuum to pick up things and transport them. Sounds strange, but how do you produce a vacuum? You use compressed air, right? So typically you use the Venturi principle to blow compressed air past a lateral crossing and you generate a vacuum in that lateral line. So this is something that is very energy inefficient because it costs you a lot of energy to compress air. Then you have leakages all the time, and then also it's a lot of noise associated with it because every time you do that, so you hear this in each and every industrial environment. So people have a desire to get rid of this. And here's one design that might enable to do away with pressurized air in the future for something like this. Here's a CAD model which has a membrane, and the membrane is lifted up by shape memory alloy wires in red over here. It's acting against a spring. So pretty much like what you do when you put your towel on the tile in the bathroom. We lift up a membrane by contracting a wire, and when we shut the current off, it cools down and the spring restores it back to its original state. So here's a prototype that comes out of the 3D printer. That's a multi-material printer which does the rigid frame and also a soft membrane at the same time. And then if you look at it, when we actuate it, watch this, the SMA wire contracting in here is deflecting the membrane that would lead to generating a vacuum. So if we move to the next one, we just place it on on a quite heavy looking piece of metal, and we don't press or anything, we just activate it by passing a current through, and you see the vacuum that you're generating is able to just lift a considerable weight, and you can just wiggle it around. It also has like all kinds of lateral force, transversal force, resistivity, and so on. So the one thing, however, is for a practical application that is still a little far away from what people in industries like, because they say, oh, we need to constantly heat it if we want to do it. And when we want to release it, we need to switch the current off, and we have to wait for the material to cool. So now the mechatronics engineer comes in and has to think about, like, how do I put the mechanisms that I have from these shape memory alloys to good use, so that I can maybe do away with some of these disadvantages. And a way to do this is here, Paul Motzke, one of our PhD students, came up with a way of using two of these wires in an antagonistic setting and placing a bistable mechanism in between. So the green is a bistable mechanism that basically just buckles from top to bottom, and then we have two wires attached here to the upper and the lower side. And the basic idea here also is that the bistable element has a pivot that it can rotate. So when I heat this wire, it applies a bending moment and on the bistable mechanism, and it basically jumps to this configuration. In this configuration, we attach it to a flat membrane, and when you then go and let this cool and heat the other wire and contract this, basically it flips through to the other side and it lifts the membrane up and generates a vacuum. Now you can switch off the current and it stays in that position because it's stable, right? So the process is, in the beginning you have two non-heated wires and a flat membrane, then you heat the lower wire and you flip up with a bistable element and generate a vacuum underneath to grip. Then you can switch off during holding. You can now, without any further energy penalty, just move things around to a different location. And if you want to release, you just go and give a brief pulse on the other wire, and then it flips back to the original side and basically releases the object that you had gripped before. So all of a sudden, low energy consumption and also very fast gripping and release because of the combination with the snapping behavior that is fast, and also the bistability that allows you for energy-free holding and operation. So how do we do this? Here's the picture of the bistable element. It's actually a cross that is pre-buckled, so it can pop out and pop into the plane of the board. And then you see the one wire is actually wrapped around several times on the top. And we do that because we increase the surface area. So if we use several wires and several winds, we have the same force that we had with a thick one, but we have a much better surface to volume ratio, so it cools much quicker, and that aids the response time. And then there is a second one, if you look closely, it's underneath. So this is basically the way how we realize this principle. Then we developed a little electronics to control all of this and 3D printed a frame and put this all together. And here's a video of how it works. And so you see the membrane from silicone right here, and you see this mechanism in the back that when you actuate it, it very quickly generates a vacuum, and then it very quickly releases the vacuum, so you can basically now very efficiently grip, move, and go to other positions. This is what we see here. So we now take it and place it on a fairly heavy piece of metal, activate it, you can lift the metal, wiggle it around and move it to different positions in an industrial process, then you release it, and you see it's very quick. Eventually we basically put this on the top of a robotic arm here, and then just went to like an industrial fair and showed it, and it's basically doing the same operation here. Now it just goes, picks something up, lifts it around, moves it to some other location, and this is a little bit for the show right here, so that we don't need pressurized air and everything. But then you can easily see during all this part you don't need any energy, and you just give it a short pulse only to release, and that is something where you can basically get an idea of how you can maybe in the future run a pressurized airless system which is energy efficient, fast, and hopefully is able to replace some of these other systems in the future. So here's another example. This is a bionic hand that we build. And this is the work of my PhD student Filomena Simone. And this is a 3D printed prototype of a hand which has also bundles of shape memory alloy wires, and we just use it to, you see here, thin wires connecting the individual digits, the phalanxes of the hand. And so there's also a protagonist and antagonist type of setup. We have bending muscles here, and then we have also stretching muscles on the upper part that go back and provide restoration. And then Reuters came and shot this movie, and we have to not just look very important, of course, but the point is I'm going to skip this here and just show you maybe the part where you see a little bit more of what it's really doing. So you see the bundles of wires working in a synchronized manner, and you see that you can grip in a very flexible way. And if you look at it, you can grip in a flexible way, you can grip strongly, but you don't have a large weight penalty. I mean, a lot of those hands have been built, but they use like little stepper motors that you integrate into the hands. You have sensors that measure, like by maybe an LVDT element, like the position of this. All of this can be done with this wire. It's right there where you need the actuation. The high energy density actually means you have a very, very lightweight actuator that does not contribute to the overall weight of the system and is still very strong. And then you can also make use of the sensing capabilities that we discussed in order to see where am I in terms of the position of this hand. And I can run a PID loop around it. I can even go and distinguish when I grip an object and try to back out with an estimator, an observer, like what the contact forces that you have. And so this is something that maybe in the future will help patients to a much better prosthetic arm, prosthetic hand that doesn't have that weight penalty or other means of, it's noiseless, by the way. So I think there's a lot of potential for something like this in the future. One, probably the most exciting applications of shape memory alloys right now is what we call elastocaloric cooling. So how does this work? I mentioned that shape memory alloys undergo a phase transformation when you stretch them and when you unload them. And in combination with this phase transformation, we always observe heats, latent heats of phase transformation to be released or absorbed. That's just like when you boil water, right? You input energy from your stove and you heat it up to 100 degrees, and then you continue to input energy, but the temperature doesn't rise, but you rather drive the evaporation of the water. And when you cool it, you get the condensation, the heat of condensation back. It's the same thing with all these phase transformations. If I'm changed from austenite to martensite, I have to input, then heat is generated, and when I go back from martensite to austenite, heat is being absorbed. And I can use that to build a process that extracts heat at a low temperature level, transports it to a high temperature level to a heat sink where it dumps the heat off, and then it cools back down, and I'm going to show you that in a second how it really works. To extract heat again, you can build a cycle to cool, just like your vapor compression driven refrigerator. Only that the interest in this is that the Department of Energy in the US and the EU Commission have basically concluded that this technology has the highest technology potential as alternatives to current vapor compression systems. And if you go back and look at current vapor compression systems, they have been optimized over 100 years by now. They're basically at the end in terms of efficiency, cooling powers, and this is where this technology now has a huge potential. And I'd like to show you basically how that can be put to work. So first thing in here is we built an experimental testing setup to do exactly what I just described. We stretch the wire where it changes from austenite to martensite, and when we unload, it changes back and absorbs heat. And when it absorbs heat, it takes heat off the heat sink, the heat source, and then upon stretching, we give it off at the heat sink. So this is the mechanics. Here's the thermal image picture of the same process, right? Here you see stretch, unload, you see how immediately upon stretching this thing heats up quite a large temperature span. So you can achieve about 20 Kelvin with respect to ambient by just stretching this wire. And then you let it cool on the heat sink, and when you restore, it drops another 20 below ambient, so that you have a temperature span of maximally 40 degrees that you can bridge with these materials. And you can nicely see how the cold shape memory alloy extracts heat from the heat source and transports it over to the heat sink. And after a number of cycles, this thing might not have been switched on. After a number of cycles, the computer dies. So, yeah, let's see. It just shut down, so I just switched on the outlet here, so maybe I can revitalize it. But basically what you saw was the process of extracting heat at a low temperature level, and then making use of the phase transformation, which by pulling brings that extracted heat to a higher temperature level. You dump it at a heat sink, and then you unload and you lower the temperature again below the ambient, and you can again extract heat. It's kind of like what your refrigerator does, right? You extract heat from the inside of the refrigerator, and then you have a compressor which brings it up to a high temperature, and at the rear side of your refrigerator you basically get rid of the heat through a heat exchanger. And let's see if I can get this thing started again here. And there's a very analogous process that you can build with a shape memory alloy wire. So what's the advantage other than the DOE being very excited about why are they? So there are two reasons. One is there's huge potential for what?
No, it was asking to confirm like the safe mode started.
Thanks. So obviously you just kind of like remote control it here. So there's a huge potential for increase of coefficient of performance. Your refrigerator has between 1 and 2. The material itself has a coefficient of performance of about 30. So it's just about how do I design a system and a process to get more out of it than the 2 that your current compressors give you, and that is how you design these processes. Okay, now let's promising. Let's get rid of this here. It's almost good. Okay, good. So it's high potential for coefficient of performance, and it is completely greenhouse free. There's no ozone depleting gases or anything. It's just solid state mechanism. I just stretch and unload and stretch and unload. There's no dangerous gases or refrigerants needed. And so this is the basic idea that I showed you. Now the question is like, how do you build a machine that does this? And this is the concept that we developed. This is my two PhD students, Susanne Marie Kirsch, Schmidt, and Margaret Schmidt and Felix Welch. And so the idea is what I just showed you, to put this in a rotary concept where a cam drive basically allows you to trigger the stretching and the unloading at the right amount, at the right angle during the rotation. And when you look at this, so while this thing rotates, the wire is being stretched. Now it goes down this little slope, it's unloaded and becomes shorter. Now it's cool. And when it runs up the slope, it's stretched, produces heat again, and becomes hot. And this is the basic idea. And the design of where these slopes are and how steep they are, that allows you to trigger the processes. So we did a lot of work on this experimental test rig within a priority program of the German Science Foundation to find out what the processes need to look like in order to be coefficient of performance efficient, optimal, or cooling power optimal. And then we use again bundles of SMA wires to have a large surface area, because you want to, basically the heat is generated in the volume, but you want to get rid of it and transmit it into the air, so you need a large surface area again here. And eventually there are many of these bundles traveling around. This is what the machine will look like eventually. And you see there's one side where they're stretched so they become hot, and one where they're unloaded and become cold. And so you put two chambers around this, right? There's one chamber where you blow air in one direction, which takes the hot exhaust air, and the other one takes the air that is being cooled and basically feeds it into the room that you want to cool. So here's how that works. There's the first prototype. You look at this. If you look closely, you see here's where it runs over the cam and is being unloaded. You look at this bundle, now it's being unloaded. Up here it's stretched, and here it's short. And when you look here, that's the same picture taken synchronously with an IR thermal camera here. And you see that whenever it unloads, it cools. Run that again. You see when the hot wire unloads, it immediately switches and becomes cold, and that is the mechanism that we put into this machine. And eventually, this is the machine, how it looked after we put it all together. Here are fans that provide the air to the cool side and to the hot side, and you see all the bundles that we discussed before. And then here's where you see the cam drive, and here's Felix. Susanne Marie was the one that operated it. These are the two guys that developed this machine. And that's currently probably the world's first prototype of an elasticalorically driven air cooler. And so this is, I think, probably the most exciting area of shape memory alloy research right now. There's a huge potential in here, and there's like a lot of interest, and there's a lot of research work to be done actually in this area. So there's some more important application-driven research that we do. You see this here, like flapping bats, right? So we also built like a bat that we actuated with shape memory alloy wires. So we mimic the flight of a bat by using muscles instead of motors. And here it's on display on the Museum of Natural Sciences in North Carolina in Raleigh, and that's basically showing how I can actuate in a biologically inspired way without using motors. So then more for some biomedical applications, back in the US, I developed what we call the smart inhaler system together with my colleague Clement Kleinstra, and we got a patent on this. And The idea here is if you inhale medication, you basically have no control over where all the aerosols deposit. Most of them get stuck in the first bend, then in the voice box, and whenever you hit a bifurcation after it enters the bronchial system, wherever there's a bifurcation, it just slams right into that bifurcation, deposits more and more. And he did work on looking at what do you need to do in order to provide a dose of medication to a tumor site. And he does a lot of modeling and CFD computations, and he did a reverse analysis. He basically looked at the particles that actually hit a tumor site that were like 2% of all the aerosols that you inhaled, and he traced them back, and he found out that they don't come from random places, but they came from a very finely located spot in the cross-section where they enter basically your oral system. And then when we talked about this, we said, well, I mean, this looks like it's a nozzle that we need, right? And they designed the system. It's what you see here. This is a nozzle inside an inhaler, and the way it works is that you do not inhale a fine mixture of air and aerosol anymore. You inhale air, and you only inject the aerosols from that location that you have found out to be relevant in order to reach a certain target in the lung system. And so we started building this within an NIH research project back then, and we could show that you could, by just rotating a fixed deflected nozzle around, you can basically determine whether it goes down your left or your right side of your lung system, or whether it goes to the 3rd generation or to the 4th generation. And then the idea here comes up that we'd really like to have this more flexible, because if you want to target different spots in the lung system, you want to be able to go to each and every arbitrary spot in the cross-section where it enters the mouth. And the idea, of course, was to build something that uses shape memory alloys and come up with an adaptive nozzle. And that's what you see here. So we built a nozzle that is driven by little SMA wires. When you look closely, you saw the wires here. There are 2 flexible joint areas in the nozzle, and there are like, each of these flexible areas has like a Mercedes star configuration of wires that when you heat them, they bend in one direction and bend it over. And you could see nicely, you can run this again. You can see nicely how you're able to actuate these wires. Here they see them, right? And there are 3 of them, 120 degrees apart, and depending on how you distribute the currents, you can move it in this direction, that direction, and you see that you can generate all kinds of shapes here. And in particular, can you bend to one side, but then you can make sure you rebend the upper part so that you're always injecting tangentially to the airstream and not generating any kind of turbulence or vorticity in here. And this is basically a system that shows nicely how you can make use of shape memory alloys, because it's almost non-invasive. It provides large deformation for actuation. By resistance measurements, we can tell where it is, which is very crucial for this application. In the beginning, we looked at it with cameras, of course, but once it's in the mouth of a patient, you cannot use a camera anymore. You need to basically rely on this internal sensing. And we could also show that we can also correlate the amount of airflow past the wire to the resistance and the power that we apply to the SMA, so that we can use it as some kind of an airflow measurement device, which is very crucial because all these ideas only work as long as the flow is laminar. So if you have too large an airflow rate, it transitions to turbulence, and then it won't work anymore. So all this can be achieved by shape memory alloy wires. And here's another biomedical application. So we have a project on smart guide wires. And so typically when you want to deposit a catheter in the patient's artery system, you have to push the guide wire through, and you have bends and bifurcations. And it's a pretty painful and cumbersome procedure if the surgeon has to place the guide wire. And one idea here is that if you want to be more flexible, you can add the same type of concept by adding SMA wires, 50 micron wires, to the tip of the guide wire. And you can move the tip around to arbitrary directions. So when he comes to a bifurcation, he wants to go right, he can just, rather than trying with a torquer and applying basically a low control method from down here, he can directly actuate the tip and tell it move right, and then he just pushes the wire through. And this will also provide a much better and more comfortable procedure for the patient, and allows it to do faster and even more non-invasive. Then we start to scale this down even more. So this is, here you see the dimensions here, 1 millimeter in diameter, 250 micrometer super elastic shape memory alloy actuated by 50 micron flexinol wires. Here is 100 micrometer core of a super elastic wire, and it's actuated by 150 micrometer muscle wire. And you see that you get like a huge amount of deformation from that one wire. So you can basically have the tip bend back onto itself. You can do it very, very quickly if you actuate it with a strong pulse so that it doesn't heat up over a long period of time. It's covered by silicone coating, and here you also saw that it's quite strong. It just pushes a coin across the table, and so this is also something where you see an application where it makes the best of all these properties that we discussed before. Yeah, with this, I think I hope I gave you a nice overview and of what you can do with smart materials, in particular shape memory alloys and a little dielectric elastomers, and you get like, again, a review of some of the applications that I showed you, and I'd really like to thank you for your attention. Thank you very much.
Questions? Yeah, Tony, back.
How even is the heating between the lengths of the wires? Like when you apply a current, does it heat up more evenly, or does it?
It completely depends. It's a thermal problem, right? It depends on whether you have convection across the wire, how homogeneous it is, and it depends on the thermal properties of the clamps. So if you clamp the wire with, let's say, a huge metal clamp, that's a heat sink. So we always have like a temperature profile along the wire, where in the middle it's somewhat evenly constant, but towards the end, basically the heat sink extracts the heat and the temperature drops to the temperature of the heat sink.
Peter?
Well, what's the efficiency of the electrical to mechanical conversion with the dielectric elastomers?
With a dielectric elastomer, it can be up to 80–90%. A lot of it depends on the electronics that we haven't talked about a lot. I mean, you have to generate high voltage, and the way that you generate the high voltage is actually one of the biggest contributors to like your efficiency that you have.
And what's the energy density of the SMA?
Of the SMAs,
Roughly, yeah.
it's 10 to the 7 joules per cubic meter. So it's roughly comparable to hydraulics, it's above pneumatics, and above all the other ones of like human muscle.
And what's the number of cycles to failure of the...
For an SMA, it completely depends on the loading, like with everything. I mean, you can get up to, let's say, 1,000 megapascals of stress from the material when you load it, and probably does that 3 or 4 times, and then it's plastically deformed. But if you limit it to, let's say, 150, 200, 250 megapascals, you can easily get 1 million cycles from it. And there has been a recent science paper where colleagues have shown that if you add like quaternary composition elements to it, you can even get like 10 to the 7 cycles without any change in the material.
You had a question?
So I wanted to ask the same question about the basically under high cycles, how much reliable they are, because
I mean,
it's based on an austenite-martensite transformation, so detwining their reversibility. So, what as you said.
Yeah.
So
and a lot of this depends on the design, the mechanical loading that I just mentioned, but also surface properties. I mean, what's the mechanism of failure is cracks, right? So if you have a very rough surface and you start under tensile loading, then you have these cracks propagating quite quickly, so you have to make sure you have very good surface properties. You have to look at the alloys. There are special ways of coming up with very low inclusion alloys where there are no additional phases where micro cracks generate and propagate, and all this kind of has to take into consideration.
Patrick, you were next.
That cooling thing, that was very interesting. In terms of sort of efficiency, if you want to use that word loosely, is it better or worse than a Peltier module, if that makes any sense?
About what?
A Peltier module?
Oh, much better. I mean,
Okay.
this is something that, in particular, then you also have to look at the temperature range, right? The Peltier elements or the Seelecke effect works well at high temperatures. But if you have like a temperature range around room temperature, the Peltier element is a disaster. And this is like orders of magnitude better.
And so in terms of competing with fridges, let's say,
Yeah.
is it
I mean-
possible to end up running those in the future, would you say?
I certainly believe so, right? This is something that we're working on right now, like the demonstrator that I showed you, the little movie. We developed some simulation models to predict like the COPs and the cooling power, and I think we should end up like probably a COP of 10, which is at least double or 3 times what we currently get from standard vapor compression system. So there's a good chance to be a lot better. Yeah.
And the only thing it needs is motion, essentially, right?
Right.
So there's sort of applications where this could be installed off-grid with nothing but a wind turbine powering it, for example.
That could be an idea if you want to cool your wind turbine park, yeah.
I was thinking, well, you're in the desert somewhere,
No.
you've got no water, you have a windmill and this condenses
Yeah.
stuff, or something like that.
Yeah, but this, I mean, this is exactly the types of ideas that you need to develop, right? It's you have to bring this together. If you look at the right application, let's say a heat engine, right? It has a relatively low thermal efficiency of several percent, but then again, if you look at the Carnot number between, let's say, 20 and 100 Celsius, I mean, that is 12% or something like that. You can't get better than that. And you're probably at 2 or 3, which is already a good fraction of the Carnot efficiency. But if you get like waste heat from industrial processes, like maybe steel manufacturing, or maybe you have a power plant where you have like waste heat at 100 degrees, you almost find no other way of converting that to mechanical energy. And if it's waste heat and you just dump it into the environment, you don't have to pay for it, then you don't care about the efficiency number, and then that would be a perfect solution to at least get some energy out of something that you otherwise throw away.
We have probably room for one more question. You had one, didn't you?
Yeah, for the SMA guide wire, you're obviously worried about the temperature the wire generates. So in the videos that you showed earlier, how much heat would that produce?
Heat or temperature?
Temperature.
Temperature.
Yeah.
See, that's the interesting question. You tend the temperature of the phase transformation is around 70 to 90 Celsius. But if you look at the energy that you input into a several micron wire and you compare it to the thermal environment of even a body and the fluid flow in the body, that is a minute amount that will be carried away almost immediately. So a lot of this goes into designing proper heat transfer systems. The heat management is very important, and that is something where a lot of this goes into why we look at bundles where if you generate enough temperature to actuate the wire and you touch it, you almost immediately extract the amount of heat element and you don't even feel it. And that's kind of like where you are. So in other words, that shouldn't be an issue if you properly drive it. You shouldn't leave the power on for a long period of time, but if you drive it with short pulses and let it cool in between, that should be no issue at all.
Thank you very much, Stefan. Stefan and Bettina are going to be with us in the lab until March,
Yeah.
I think. So you can, if you want to strike up a conversation, we're on the 5th floor of the ABI. Look for me, or and I'll bring you down to them. And Bettina is also working, and I think Bettina will be giving a seminar later on. Probably toward the other side of the state. And yeah, so thank you very much for your talk, and it was very, very enlightening. Thank you very much.
Thank you.
Let's scoot over here. So.